Hello, and welcome again to my Physics Online video lecture series. Today's video, we're going to be discussing Faraday's law, which is a continuation of, and in some sense, a generalization of the discussion we've been having about the bar moving on a set of conducting bar on conducting tracks in a magnetic field. Now, from motional EMF, we were able to obtain the result that the induced EMF was equal to the distance between the two tracks, we'll call that L, times the magnetic field strength B times the velocity vector V magnitude, so we'll say LVB, times the sine of the angle between V and the magnetic field. And in this case, you have a counterclockwise current as a result. But this could be generalized to E induced was equal to the magnetic field dotted with the derivative or the rate change, of the area vector per unit time. And again, this right here could be further generalized by noting that there could be N of these rods sliding together in sequence along N of these tracks. And we could throw a minus sign in front. None of that should be especially concerning. Now, the furtherance of this, so this would basically look like negative N times B times delta A over delta T times cosine of the angle phi between A and B. So again, if I have an area vector and a B field vector like this, maybe here's area and here's magnetic field, then this is angle phi. If I have a velocity vector and a magnetic field vector, V and B, then this is theta. And looking at these diagrams, it turns out that theta and phi are going to therefore be perpendicular to each other in some way. Faraday's law basically takes this equation right here and further generalizes it. For example, maybe I happen to have a coil of wire like this that has N turns in it. So maybe it's like a solenoid or what have you. And maybe I happen to have a magnetic field sort of in and around that coil of wire. So maybe this right here represents my magnetic field. It's supposed to be a uniform field, although it doesn't necessarily have to be that either. It just kind of helps if what you're trying to do is an algebra-based problem. So here's a sort of uniform field. I'll just draw it via good old copy and paste. And essentially, you could see that the area vector for the coil of wire, I'll draw it in sort of these blue lines, area A, would have to either point out or point into the plane of the screen, since it's got to be perpendicular to the surface being enclosed. Now, in this previous example, I'm essentially decreasing or increasing the area. But what if I leave the area alone and instead increase or decrease the magnetic field strength? Well, it turns out that if that happens, I end up getting also an induced EMF. For that matter, if I rotate the coil so that the area vector, rather than pointing out of the screen at you, rotates slowly so that it is, say, parallel to the plane of the screen, then that also induces an EMF. So if I take this same thing and rotate it, maybe about this axis or about this axis, it doesn't matter, as long as the whole area vector is sweeping, then that also induces an EMF. If you put those two things together with the induced EMF also being the rate change of A over T, then what you end up getting is this. The induced EMF on average is the negative of the number of turns times the rate change of the flux phi b per time, okay? Where phi b, this flux, is simply defined as b dot A, and where there are in turns of wire, in loops of wire in this coil. So this is what's called Faraday's law, and the minus sign in it you could think of in some sense as a consequence of the right-handed rule from this particular problem, but what it actually does, so the minus sign, what it actually does is it is itself a law. It's what's called Lenz's law. And what Lenz's law says is that if we come back over here, for example, you could get an induced current from Ohm's law, which would be the induced EMF divided by the resistance. And if you induce a current, so induced current produces a magnetic field. And so this would be like B induced. And what it does is that it opposes the change in flux from the original magnetic field. So if we were to go back to our original little diagram here, you have an induced current. You can use the right-hand rule for each sort of like side of this circuit to figure out what direction the induced magnetic field will be pointing in. Or you could use the right-hand rule and wrap your fingers around the direction that the current is pointing in. Either way, what you'll end up getting is that your induced magnetic field is pointing out of the screen, because if you ignore the induced magnetic field as the bar is moving, you're basically getting more and more of these field lines into the screen enclosed in this rectangle. And so the induced magnetic field points out of the screen to sort of like conserve the total number of field lines enclosed. Now, it doesn't quite necessarily entirely conserve, it just kind of slows the rate of change down. So if I were to do B induced dot area, that right there should be less than but equal to the rate change of B dot area. And essentially, this means that it's typically the less than. So let's go ahead and kind of circle this less. It's typically less than, but it has the opposite sign of. So this would be negative if this is positive. This would be positive if this is negative. And note that it's the dot product that is positive or negative, not the individual fields. That's true over here too. If I were to start decreasing my magnetic field strength, then my induced field would have to point into the plane of the page. If I were to start increasing my magnetic field strength, then the induced will point out of the plane of the page, simply because the original field is into the page. If I start rotating the coil instead, then my induced EMF will tend to point, like let's say that the coil is originally oriented this way, and so now I move to be oriented this way. The original flux would have been, from your perspective, like into the screen. And so basically, as I rotate this area vector like this, the induced field will point this direction. Quick example, and then we'll wrap up. All right, so for this example, I have also a diagram, which is essentially the same diagram as what I showed up here. We're just kind of putting some numbers to it. So we're reducing from 2 to 1 Tesla. We have an area, we have a number of windings, we have a time. The induced EMF should look like negative N delta B dot A over delta T. Remember that B dot A is the change in flux. So this is negative 300 times, essentially the delta is the change in B. So if we were to write this out again, be negative N times delta B times A times essentially like the cosine of the angle between the two, divided by delta time. This term right here is actually negative 1 because the area vector is out of the screen, the B field is into the screen. And so my induced EMF is going to be 300 times 2 minus 1 Teslas times 0.25 square meters divided by 10 milliseconds, which is 0.01 seconds. So my induced EMF in this case comes to basically 7.5 times 10 to the 3 volts, all told, or 7,500 volts. And as far as the fact that it's a positive number, what does that mean? Basically means that I expect the current to be counterclockwise and the induced EMF to actually be into the screen in this case. Sorry, the current will be clockwise, excuse me, and the induced B field will be into the screen. And so that's it. That's an example, and that's all that I'm going to cover in today's video. So thanks for watching, and I hope that you've learned something from this video, and stay tuned for the next one.